Okay, our next speaker this afternoon is Tanja Gernhard from Munich, and she's going to talk to us about new analytical results for the speciation times in neutral models.
Yeah, hello. Yeah, I'm doing my PhD currently in, is this on? Yeah, okay. In Munich, and actually I just changed the title, but I'm talking about the same. So, tree shapes induced by neutral models for speciation. And now I don't know how to just. Yeah?
That one is. That one.
Okay, and this is.
And that's your light. There.
Okay. Sorry about that. So, yeah, tree shapes induced by neutral models for speciation. So, neutral models, first of all, models for speciation is we want to describe how species evolve. So, how long do they live before they give birth to new species, let's say, or they go extinct. And neutral models are, their species are considered to all behave alike. To make this more precise, this is normally modeled by a constant rate birth and death process. So in any point of time when we see a species, it has an exponential lifetime and dies with a parameter mu. And during this lifetime, it gives birth to new species according also to an exponential distribution with parameter lambda. And actually, this birth and death process have been investigated quite a bit. But the new thing or the crucial thing I want to point out is I want to condition those processes to have n species today. Because, I mean, if you have a data tree, you also have, let's say, 50 species in your tree. So you know how many species there are. So you want to condition this process after a while to end with 50 species. And here I brought you, this is just an example tree which is induced by such a birth and death process. So you have the time of origin, your first species lives for a while, and then it splits into two new species. And then those two lineages behave independently. You have this birth rate lambda that you get new species, and then with the death rate mu, you go extinct. So for example, this species got extinct. And then here you would end up with 5 species, so n equals 5. And in the following, actually, I don't want to consider this whole tree, but I want to consider this so-called, people called it reconstructed tree. That is, you take the tree from the birth-death process, delete all the extinct lineages, so you have a tree just on an extant species, so the leaves. And this is actually what we see when we reconstruct trees from data if we don't include the fossil record. So we just see the extant species. And we can ask questions like, well, yeah, how does the shape of this tree looks like? And with shape, I don't only mean the topology, but also the edge length. So at what time did those events happen? So for example, at what time did the most recent common ancestor of those 5 species evolve? And so what is the expected time or the density for this point? Or then the second speciation event, which could have been this or that event, at what time did that occur? Okay, so how are we going? And I want to point out for the topology, I'm not going to talk about the topology distribution at all, because there's a known result that for any parameters lambda and mu, if we just look at a reconstructed tree, the distribution is the same. It's all like in the U model. So the U model is when we don't have extinction at all. So we don't have to, so the topology distribution is well known. Okay, and what can we say about the time of the speciation events? So this is again our reconstructed tree. And first of all, we can notice that if we just draw on the x-axis, basically the leaves, we can put for the speciation times points in between 2 adjacent leaves. And if you then look at what times those SI evolved, you can we established that they are actually IID distributed, so they're all independent and have the same distribution. And the distribution for those SI is this big expression. So here it's not really important how this expression looks like. The only thing what we should note here, that here it's conditioned on the time of origin. So when did the first species evolve? And in the following, so this is kind of, well, nice. We now know when those SIs evolved, but I promised you that I want to know when the most recent common ancestor, for example, evolved, or when was the second speciation event. And then I, on top, want to get rid of this conditioning on the origin of the tree, because this is something we don't really know. And it actually depends if we choose lambda and mu smaller, then the origin of the T would become smaller or bigger, actually. So I use this has been done a lot before in simulations. You just use a uniform prior for the time of origin. And then you can actually establish the density for A and K, the time of the K speciation event in a phylogeny with n extinct species. And this is this quite complicated density function. However, for the U model, where we don't have extinction, it looks a little bit nicer. And the other special case is the so-called critical branching process, where the birth rate lambda equals the death rate mu. We also have a slightly nicer expression. So now for k equals 1, that would be the most recent common ancestor, we would know with what the distribution when it appeared in our reconstructed tree. And from that, we can also establish the expectations. So this is the general expectation, which is quite messy. But then in the U model, this was known before when you only have speciation and no extinction. We have a quite nice expression, and in a critical branching process, it also becomes all really nice. So what can we do with those expressions? If we have a given phylogenetic tree, we might be interested, and which is not dated, we might be interested according to specific lambda and mu, at what time did those speciation events occur. And with the knowledge of the distribution of the topology of those trees, we can now actually date the whole tree. So this would be under the critical branching process, the one extreme case, and that would be under the U model, the other extreme case. So only the topology is known, and then assuming a first death process, we can date the vertices. I mean, normally, I guess nobody would date a whole tree, but in super tree reconstruction, sometimes some vertices are undated, and then what people actually did, they assumed the U model, simulated the edge length, and then dated an unknown date with the expected time under the U model. So this could be now done without simulations, and also for models which include extinction. However, I don't want to talk much more about the dating stuff now, but you could also use those expectations for lineage to time plots. So lineage to time plots are frequently used to compare the time in, so in dated phylogenies, you see, you plot basically the time against the logarithm of the number of species and compare it to, under the model, how those plots would look like. And now we can actually, since we know the expected time of the first speciation event, second speciation event, and so on, we can actually, this would be for the critical branching process. At 0, we had the most recent common ancestor. And then the first speciation event was at n-2 divided by 2, I suppose. And we plot that here, draw a straight line, and so on, take the third speciation event, fourth speciation event. So that would be the line for the critical branching process. And then we go up, and the green line would be the U model. And in between, we have decreasing mu. And so people actually use those lineage to time plots of the model, and then plot what the data gives them, and then compare this. Okay, so this would be now analytically and without simulations. However, I called it already the horizontal lineage to time plot. So what I'm actually now here doing is I go up the y-axis and then look at what time did I observe that many species. But an alternative way would be I go down the time axis and look, well, when 0.3, the fraction 0.3 of the time evolved between the most recent common ancestor and today, how many species do I expect at that time? And that we then could also calculate analytically. And this now is a really, for me, it was a surprising plot. So first, I said I always condition on observing a certain number of species, in my case, 10 species. And now first, I also conditioned on having time t evolved since the time of origin. And then, so the first, the color should, well, the first line, the most convex line would be this green line. It's actually the U model. Lambda equals 5 and mu is 0. And then we keep lambda to 5 and increase mu to lambda divided by 4 would be the yellow line. So the lineage to time plots get less and less convex for increasing mu. And if you looked at what other people did in lineage to time plots, it looked the other way around. So people before conditioned just on a time since origin t, and then simulated trees until t, calculate the expected number of species, and then plotted those results. At there, you have a straight line for u, and then more convex plots for mu increasing. But there, you didn't condition to have 10 species. Though I expected before I would see a similar pattern than if I just condition on t. And first I thought probably I did a really stupid mistakes in my calculations. But then actually I thought, well, I can get rid of the n equals 10. I just sum up over all possible n's. And then I would only condition on t. And I ended up with exactly the same results which were existent for just conditioning on t. So I was sure this must be right. But I can't really interpret it yet. So if anybody has some thoughts on that, I would be happy to talk about that later. And now, but I promised you at the beginning I don't want to condition on t, actually. So I integrated over all possible t's and then came back to some actually nice plot again. So now this black line is the critical branching process, and when I decrease mu, I get less and less convex. That's what we see in other lineage to time plots as well. Though normally the U model, when we condition on the time since origin, the U model gives the straight line. And here, if I condition on n equals 10 and don't care about time since origin, this is a slightly convex curve. And I guess what I just want to point out here is people use the lineage to time plots to actually estimate the birth and death rates, lambda and mu. But I think one should be careful and has to decide on what I actually have to condition or should condition, because when people normally look at the data and it's a little bit convex, then you would expect that it's not a pure birth process, because the U model, if I condition on t, is the straight line. But then if you condition on n, the number of species, the U model is actually not a straight line anymore. So there's some discrepancy. And this should be kept in mind, I think. Yeah, so with this little confusion or different results on lineage to time plots, I want to end and say thank you to Mike Steele and Dennis Wong for discussing some of the issues, and my advisor, Anush Taras, and my funding, and the whole New Zealand group. Thank you.
Any questions? Yes?
I might have missed something, but how do you learn lambda and mu when you don't have them? Is there any learning methods for them?
Oh, okay. So what people do if they, so if you condition your lineage to time plot on having that your trees have the age t origin, then actually the first part of your lineage to time plot is a straight line which increases with lambda minus mu. So the increase of the line is lambda minus mu. And then the second part, so it goes first straight, and then it makes a curve and goes much, much steeper. And that how do you say? The Steigung? Slope. And then the slope is lambda. So you can look at the very end here. This slope should be lambda, and the first slope should be lambda minus mu. But that is assuming that you condition on the age of your tree and not on how many species you observe. And that's where I think there's a problem.
Yeah.
But that's how it's done.
From n, exactly, from n, how you
So from n, I don't know of that people did it, or how they, and simulations would actually be quite tricky because, for example, for the critical branching process, with probability 1 it would go extinct, and so actually observing a tree on n species you need rather a lot of simulations to get that. So I'm not sure. I looked around a lot, and I've not seen that people actually compared the data to the lineage to time plots condition on the n, but they compared to the lineage to time plots conditioning on t. And there it's straightforward with the lambda minus mu and the lambda slope.
Okay, thank you very much. And we'll have our third speaker.